Welcome to the debate. Imagine a universe that expands infinitely, right? It just grows colder and emptier until time itself literally ceases to have any physical meaning.
Right, the classic heat death scenario.
Exactly. But then, and here is the incredible part, imagine realizing that this exact moment of infinite freezing emptiness is mathematically identical to the explosive, fiery birth of a brand new universe.
It is a beautiful concept, theoretically speaking.
It really is. And today, we're looking at a five-dimensional model that claims to provide the mathematical scaffolding for exactly that phenomenon. It's a model driven by a novel, split quaternion-like extension of the complex plane.
Yeah, which generates a full 5D orthogonal transformation.
Right. The sheer ambition here is staggering. Doing this natively in the algebra, it immediately raises a critical question for theoretical physicists.
It absolutely does. Because, while the idea of a universe cycling through aeons is philosophically beautiful, we have to be ruthlessly pragmatic about the underlying math here.
Always.
So the central question we have to answer today is this. Does the definition of the time-dependent ultra-speed parameter in this model, what the author calls v of t, does it actually represent a mathematically rigorous foundation for a new conformal cosmology? Or is it merely an ad hoc algebraic ansatz, something manually reverse-engineered just to fit the observations we already have?
Well, I argue that extending the complex plane to define a 5D orthogonal transformation mathematically necessitates a metric that elegantly resolves into a conformal cosmology, one that naturally matches both our current lambda CDM observations and Sir Roger Penrose's conformal cyclic cosmology.
And I argue that while the algebraic structure of the 5D space is undeniably novel, I'll give it that, manually forcing that parameter v of t to follow a specific exponential time evolution curve completely undermines the physical rigor of the model.
You think it breaks it?
I think it renders it an exercise in mathematical curve fitting rather than foundational, fundamental physics.
Okay, well, to really appreciate what this model is doing, we have to start at the bedrock, the foundational algebra. Because in standard complex numbers, if you try to solve the equation z times its conjugate equals -1, you just hit a brick wall.
Right, there is no solution in the standard complex plane. It's impossible.
Exactly. But this paper introduces a rigorous extension where that solution does exist. It basically creates a multi-vector algebra that's highly reminiscent of Clifford algebras, where conjugation acts as an involution.
Which gives us that canonical basis.
Right, a basis that behaves exactly like the hyperbolic nature of space-time natively. You don't have to, manually inject minus signs everywhere to get a Lorentzian signature. The algebra just handles it inherently. And the real magic happens when we apply an orthogonal transformation to what the text calls the 5D spacetime ultra.
Right, the lambda transformation. Look, I'll hand it to the author. The structural elegance here it's undeniable.
It really is beautiful.
The way that transformation preserves squared lengths and maintains strict orthogonality across all 5 dimensions is incredibly neat. But we have to look closely at what happens when you actually extract the physical metric from that pristine geometry.
Okay, let's look at it.
The operation generates a 4-position tensor, right? And from that, we get our Lorentzian metric. But if you look at the diagonal of that metric, the time component scales inversely to v of t, while the 3 spatial dimensions scale directly with v of t.
Exactly. It acts like a mathematical accordion. As time marches forward and this parameter v grows, the time component essentially stretches out while the 3 spatial dimensions, they scale in perfect harmony.
But that's exactly...
Wait, just to finish the thought. We don't have to artificially add a cosmological constant by hand to force the universe to expand here. The algebra beautifully yields these Friedmann equivalent equations right out of the box, just from the geometry itself.
Yeah, but that's exactly where my skepticism kicks in. I come at it from a different way. You cannot decouple that beautiful geometry from the physical constraints of the v of t parameter.
How so?
Think about what that metric physically demands. For the scaling factor to make any sense at all, without completely breaking causality outside of some very specific boundary conditions, v of t must live strictly between 0 and 1.
Right, it's bounded.
Bounded, yes. Now, the math of the split quaternion extension doesn't naturally mandate the specific exponential form the author uses, right? Where v of t equals 1e to the lambda t. The math doesn't give you that.
Well, it gives you the bounds.
Plugs in a convenient exponential function to satisfy them artificially.
I see why you think that, but let me give you a different perspective. Think of v of t like the early scalar field potentials we used in the early days of inflationary cosmology.
Oh, the inflaton fields?
Exactly. Was the initial inflaton field an ansatz? Yes, absolutely. We all knew it. But it was an ansatz that allowed us to explore a deeply symmetric underlying geometry. The structural framework of this 5D space holds up regardless of the specific curve you plug in for v.
I don't know if I agree that it completely holds up.
I mean, even if we concede that the specific exponential curve is a toy model meant for numerical calculation, which, by the way, the text explicitly acknowledges, the existence of the metric itself is profound.
Profound, sure. But it's reverse engineering. It's like designing an incredibly complex, beautiful gear system for a clock, but then realizing the hands don't move right.
That's a bit harsh.
No, think about it. So instead of fixing the gears, you just tape a battery-powered motor to the clock face and force the hands to spin at the exact speed you want. The multi-vector geometry is the beautiful gear system, but 5T is that taped-on motor.
I disagree.
If the geometry is truly fundamental, the time evolution of the scaling factor should emerge dynamically from the field equations themselves, not be manually inserted just to make the integrals behave.
I wouldn't call it a taped-on motor when the geometry strictly dictates the boundaries of how that motor can even operate. I mean, look at the metric loosening transformation the paper describes.
The gamma transformation.
Right. When we take this 4 tensor and place it on a 5D grid with time, the 3 spatial dimensions, and this new 5th dimension W, we get a Ricci flat metric.
Yes, which is mathematically convenient.
It's more than convenient. As theoretical physicists, we know how incredibly rare and highly sought after a naturally Ricci flat metric is. And if you calculate the Einstein tensor for this space, specifically the GT component, it emerges entirely from the frame dragging term between time and that 5th dimension.
You're talking about the B of T term.
Right. The B term, it's essentially a temporal spatial frame dragging. And when we set the Einstein tensor to be identically null to maintain that flat geometry, we find that V must always be positive and it must be growing between 0 and 1. The geometry is dictating the physical boundaries of the parameter. It's not arbitrary.
Dictating the boundaries perhaps, but certainly not the dynamics. It tells us V has to rise from 0 to 1. It does absolutely nothing to give us the mechanism of how it rises.
But it narrows the field of possibilities immensely.
Does it? And that frame dragging term you just mentioned, it only yields a null Einstein tensor if we strictly obey a very specific relationship. If we require a local time-like killing vector to ensure conservation of energy in that space, we are mathematically constrained to setting B equal to the derivative of V divided by V.
Which is a clean constraint.
But look what it does. It yields an Einstein tensor where the GT component is fundamentally just a ratio of the derivative of V squared over V squared. Notice how every single cosmological outcome, every single tensor component, is entirely subordinate to the first and second derivatives of V of t.
Because V of t is the driving engine of the expansion.
Right, but you haven't discovered the fundamental engine of the universe. You've just pushed a beautifully crafted chassis down a hill and claimed gravity as a feature of the axles.
Okay, but you can't look at this metric in a vacuum. If you follow the logical breadcrumbs of that geometry, it forces you into some wild physical implications. Specifically, conformal cosmology.
Ah, here we go.
Let's trace what happens when you push this metric to its absolute physical limits. Because the inverse metric gives us a time component of -1 over V of t and spatial components of exactly V of t. Taking the inner product yields a squared scale factor that is inextricably linked to V.
Right, a squared t.
Exactly. It becomes V of t divided by 1 minus V of t squared. When you plug in the exponential profile, the result maps perfectly onto Penrose's conformal cyclic cosmology.
And this is where the mathematical sleight of hand really happens.
It's not sleight of hand. It's a natural limit. Look at the asymptotes. As time goes to positive infinity, the metric seamlessly smooths out into the standard Minkowski metric, -1, 1, 1, 1. It becomes perfectly flat, empty spacetime.
Sure, at infinite time.
But if we run the exponential clock backward in time to a specific finite negative value, exactly at t equals negative natural log of 2, the squared scaling function flips sign. The entire causal structure of the universe inverts to +1, -1, -1, -1.
Right, the famous causal flip.
Exactly. Why negative natural log of 2? Because when you run the clock backward to that exact moment, the value of our speed parameter v of t hits a critical threshold that inverts the entire metric. Suddenly, time acts like space, and space acts like time.
It's an interesting mathematical curiosity, yes.
It's a mathematical looking glass. It provides a rigorous, completely conformal boundary between eons. The infinite, freezing future of one universe is mathematically indistinguishable, metric-wise, from the singular genesis of the next. It's a stunning realization of Penrose's dream that the universe resets its entropy by essentially forgetting its scale.
I'm sorry, but I just don't buy that. Let me tell you why.
Okay, tell me.
The conformal mapping you're praising as some deep, universe-revealing physical insight is nothing more than an algebraic artifact. It's an artifact of the specific equation the author chose for v of t. You're marveling at a reflection in a mirror you set up yourself.
How is it just the reflection? The limit behavior natively supports the causal inversion.
Because of the algebraic structure of the function you inserted. The relationship between the negative time before the Big Bang, let's call it t minus, and the positive time in the distant future, t plus, is symmetric purely because the underlying algebraic function h of u equals u minus 1 to u minus 1 happens to be its own inverse.
Well, yes, it's an involution.
Right, it's a well-known algebraic property. When you substitute those exponential functions back in, of course, t minus is going to equal the natural log of the inverted exponentials of t plus. It is a mathematical tautology.
I wouldn't say tautology.
You plug in a self-inverting mathematical function, and shocker, you get a self-inverting boundary condition at the end of the universe. To claim this is physical evidence of conformal cyclic cosmology is to mistake the map for the territory, especially when you intentionally drew the map to look exactly like the territory.
It's not just the conformal boundary that works out, though. Defending the physical implications of this model requires us to look at the thermodynamics, specifically the energy-momentum tensor and the Friedman-like equations derived from it.
Okay, let's look at the thermodynamics.
Look at how the density and pressure of the universe evolved in this framework. They aren't arbitrary. They are defined strictly by v of t, its derivatives, the spatial curvature k, and the cosmological constant, lambda. Because v of t smoothly limits to exactly 1 at positive infinity, its first and second derivatives gracefully go to 0.
Yes, because it's an exponential asymptote. Of course the derivatives vanish.
But look at the physical consequence of that. It gracefully yields finite, well-behaved cosmological parameters at infinity. The density at infinity perfectly resolves to -3k plus lambda, and the pressure resolves to -k plus lambda.
Assuming those parameters hold constant.
Right, and if we set the curvature equal to the cosmological constant, the model successfully yields a perfect dust-like behavior at the end of time. It even naturally recovers the thermodynamic continuity equation. This isn't just an algebraic artifact. It is a fully consistent thermodynamic and gravitational evolution stemming directly from a 5D metric. You can't fake a thermodynamically stable universe just by picking a lucky function.
It is internally consistent, yes, but again, that consistency hinges entirely on the first and second derivatives of v of t cleanly zeroing out.
Which they do.
Because of the exponential. If v of t oscillated as it approached 1, or if it had, say, a power law approach instead of an exponential one, your universe's density and pressure would behave wildly. They might even diverge. The thermodynamics only look stable because you pick the most stable possible mathematical function to drive the engine.
But that's exactly how theoretical physics progresses. We find the mathematical constraints that produce the universe we observe, and then we work backward to find the fundamental source of those constraints.
I agree with the method, but let's look deeper into where these implications lead us when we try to bridge the gap to quantum mechanics. If you really want to evaluate the physical implications, we have to talk about the D'Alembert operator.
Ah, the box operator.
Right. The box operator applied to a scalar field on the compactified fifth dimension,
Equation.
A bridge built on sand, unfortunately. For the listeners who might be rusty on Kaluza-Klein theory, let's contextualize this quickly. Back in the 1920s, physicists realized that if you add a fifth dimension to general relativity, and you wrap that fifth dimension up into a tiny unobservable circle, the resulting math naturally spits out electromagnetism.
It's a beautiful concept.
It is. In this paper, the author applies a scale factor transformation to the wave function, essentially tying it to that time-dependent v parameter, and wraps the fifth dimension into a tight circle with a specific radius.
Right, and the derivation naturally yields an effective mass for the quantum field.
It does. It yields an effective mass that equals v squared times the winding number divided by the radius of the curled-up dimension. It is structurally fascinating to see a constant potential and a time-dependent effective mass emerge purely from a 5D classical metric. But we have to ask, what is its actual physical utility?
Well, it gives us a quantum framework.
Does it? The effective Hamiltonian, the effective mass, the quantum behavior. It all fundamentally relies on the time dependency of VT. If VT is merely a toy model, then your beautifully derived effective Schrödinger equation is just a toy equation describing a toy quantum field. It cannot make hard, testable predictions about particle physics if the foundational parameter driving the time evolution is a hand-picked choice rather than a derived field.
I think characterizing it as a toy equation severely diminishes the power of finding a Schrödinger-like equation embedded natively in a classical metric. Let's think about the physical implications of that effective mass equation you just mentioned.
Okay.
The mass term is proportional to v squared. What happens as time goes to infinity? Because v asymptotes to 1, that mass term settles exactly at the winding number divided by the radius. It gives us a perfectly stable, quantized Kaluza-Klein mass spectrum at the late stages of the universe.
Again, assuming v of t behaves exactly the way you told it to.
Even if v of t is an ansatz in this specific draft of the theory, its required boundaries, starting at 0, being strictly bounded by 1, with vanishing derivatives at infinity to ensure thermodynamic stability, these are incredibly tight physical constraints.
That I will agree with.
Right. Any future fundamental theory of quantum gravity that eventually derives v of t from first principles will have to fit within that exact envelope. The mathematical framework has essentially built the exact scaffolding needed for the physics to snap into place. It's basically telling us, if you want a universe that matches quantum mechanics, thermodynamics, and conformal cyclic cosmology, your parameter must look exactly like this.
I will grant you that it is an impressive scaffolding. The fact that the Kaluza-Klein mass spectrum emerges cleanly at the infinite limit is a genuinely nice touch, and it shows the author deeply understands the intersection of these fields.
Absolutely.
But as theoretical physicists, we have to demand rigor all the way down to the bedrock. We cannot allow an ultra-speed parameter to act as a mathematical deus ex machina. It resolves the Big Bang singularities, it perfectly matches the conformal boundaries, and it neatly ties up the energy-momentum tensor. But it only does all of that because we manually forced it to.
You still think it's too phenomenological?
Yes, the split quaternion extension gives us a genuinely fascinating geometry, and the Lorentz-like transformation into the extra dimension is handled with incredible algebraic precision. But until v of t is actually derived from an action principle, where, emerges dynamically from the field equations themselves, this remains a phenomenological model. It describes what we want to see rather than explaining why it must be so.
Well, let's synthesize our positions as we look at the totality of this model. From my perspective, the framework presented here, leveraging a 5D Lorentz-like transformation rooted in an extension of the complex plane, provides an incredibly fertile mathematical ground.
It is fertile, yes.
From pure geometry, it naturally produces a valid Lorentzian metric. Without arbitrary adjustments or adding forces by hand, it gives us the cosmic scaling factors, the Friedmann equivalent equations, and the stable thermodynamic continuity equation. Crucially, it yields those conformal boundaries that flawlessly mirror Penrose's conformal cyclic cosmology, mapping an infinite, expanding future to a singular causal flip at exactly t equals minus ln2. To me, it represents a profound, mathematically rigorous unification of special relativity, general relativity, and conformal geometry.
And to synthesize my view, while the algebraic extension of the multi-vector space and the subsequent tensor mechanics are undeniably precise and elegant, the physical edifice built upon them remains structurally suspect. Everything from the mimicking of the lambda CDM scaling factor to the stable thermodynamics at infinity, right down to the effective Schrödinger mass hinges entirely on the behavior of VFT.
Right, the core of our disagreement.
Exactly. Because this parameter is a phenomenological plug-in, a deliberately chosen exponential curve, rather than a true physical derivation. It currently lacks the rigorous first principles justification required of foundational physics. It is an exercise in beautifully fitting a curve to a desired outcome.
Even with those reservations, there is no denying the sheer mathematical beauty of how that conformal boundary matches the infinite future to the singular moment of creation. I mean, the causal flip, where space-time literally inverts its signature, remains one of the most compelling and thought-provoking aspects of the model.
Oh, it is incredibly elegant. And I think we both agree that the true test of this theory lies ahead. The theoretical physics community will need to really dig into this geometry and determine whether the time dependency of VFT can actually be derived from the fundamental physics of the 5D space, rather than being inserted by hand to make the integrals work out.
Exactly. The geometry is waiting for the dynamics to catch up. The abstract symmetry is there, perfectly balanced on the page, but we are left asking the ultimate question: does the physical universe actually follow this beautiful math, or are we just guiding its hand to see what we want to see? That is a question we will leave for you to consider.